From adapting vision models online as new domains and unknown classes appear, to exposing backdoors by turning poison samples into a detectable pattern, and even teaching AI to perceive and generate the speed of time in video, today's papers all share one theme: learning to handle change. In this episode, we dive into 3 striking ideas that push models to become more adaptive, more robust, and more aware of motion, uncovering how subtle shifts in data can unlock big leaps in performance. Let's explore the first paper, Back to Source Open Set Continual Test Time Adaptation via Domain Compensation. Back to Source introduces DOCO, a prompt-based framework for open set continual test time adaptation, OCTTA, where a model must track non-stationary domain shifts while unknown classes appear online. The key novelty is domain compensation. DOCO first splits each batch into likely in-distribution and out-of-distribution samples using prototypical distance to frozen source class weights and k-means, then updates only a small set of visual prompts on the likely ID subset to match cache source feature mean and standard deviation, while preserving pairwise cosine geometry through a structural regularizer. The updated prompt is immediately propagated to the likely OOD samples in the same batch, so the same batch-level domain factor is removed from both ID and OOD features, making semantic novelty separable again. This creates a closed-loop mechanism in which better split quality improves prompt learning and better prompts improve future splitting. The method is implemented on VIT-B16 with visual prompt tuning, typically using 8 learnable prompts and a single online grading step per batch after a 5.0 iteration initialization on 300 source samples. On ImageNet-C under Okta with 50% OOD ratio, DOCO reaches 61.5% accuracy, 82.7% OOD-OCK, and 70.1% H-score, outperforming Unient by 4.7 H-score points and DP Core by 7.5 points. On the harder Leon-C benchmark, it attains 32.7% average H-score, 2.4 points above the next best method. Ablations show statistical alignment alone is insufficient. While adding sample splitting and OOD propagation gives the largest gain, the full structural regularizer further lifts performance. Let's explore the second paper, CSC, Turning the Adversary's Poison Against Itself. CSC, Turning the Adversary's Poison Against Itself, argues that poisoning-based backdoors create a train time separability artifact that defenses can exploit rather than merely suppress. The authors analyze latent dynamics of DNN training and show that, early in optimization, poison samples already form isolated clusters in representation space because the trigger becomes the dominant predictive feature. Later, the classifier head hardens a trigger-to-target association. CSC, for cluster segregation concealment, turns this into a 2-stage defense. It first trains normally, then extracts penultimate layer features from the first 10 epochs, reduces them with tsni, and applies dbscan EPS equals 3 to detect anomalous clusters using class diversity and density criteria. Samples in suspicious clusters are treated as poisoned, then relabeled to a new virtual class. In the concealment stage, CSC freezes the feature extractor and fine-tunes only the classifier head for 10 epochs with cross-entropy on the augmented set, replacing the adversarial trigger target link with a benign trigger virtual class link instead of unlearning it. On CFAR 1.0, CFAR 1.0.0, GTSRB, and Tiny ImageNet with ResNet 1.8 CSC was tested against 12 attacks, including BadNets, Trojan, BlendStrip, BlendKitty, AdaptBlend, SIG, CL, ABS, IAB, WANET, and SSBA, and compared with 9 defenses including ABL, DBD, DST, NON, CBD, ASD, DPSGD, and NAD. It drives mean ASR to 0.02% on CFAR-T, 0.08% on CFAR-100, 0.9% on GTSRB, and 0.06% on Tiny ImageNet, while preserving clean accuracy, with only small average drops of 0.29%, 1.18%, and 0.65% on the first 3 datasets. Poison segregation itself reaches its greater than 98% precision and is greater than 94% recall on almost all attacks. And the concealment module retains much higher accuracy than unlearning-based removal, which can collapse models. Let's explore the third paper, Seeing Fast and Slow, Learning the Flow of Time in Videos. Seeing Fast and Slow treats time as a directly learnable visual variable rather than an implicit nuisance factor. The paper's core contribution is a self-supervised framework for inferring playback speed from video, then using that capability to build and exploit slow-mo for 4K, a new large-scale slow-motion dataset with 44,632 clips and 18 million frames, which is over 70 times larger in videos and 150 times larger in frames than prior high FPS collections. For speed change detection, the method extracts free supervision from audio via time-frequency scaling. When playback speed changes, audio pitch shifts, a video MAEF2 base detector trained on these audio line labels reaches 92.4% accuracy, far above Gemini 2.5 at 59.5% and a CRAFT optical flow baseline at 80.4%. For absolute speed estimation, the paper introduces an equivariance objective under temporal resampling, enforcing that predicted speed scales proportionally when clips are accelerated or downsampled. With calibration from a small set of labeled videos and a 3-iteration refinement scheme, the model achieves Pearson correlation 0.735, Spearman 0.706, RMSE 0.649, and ERMSE 1.913 inches log space, approaching human performance much more closely than video LLM, SpeedNet, or Pulse of Motion. The dataset then enables 2 generation tasks. First, a speed-conditioned WAN2, 1I2V model learns to synthesize motion at explicit rates from 0.01 times to 1 times using logarithmic speed buckets and frame-wise speed conditioning, outperforming prompt-only control and trajectory-based ATI with better FID, FVD, and stronger optical flow monotonicity. Second, a WAN2, 1 VACE, based temporal super-resolution model reconstructs high FPS video from blurred low FPS input, improving over film, LDM VFI, and generative in between. On slow-mo Neliaku test, it reduces flow pips to 0.067 and FVD to 134.3, while human raters prefer it in over 90% of real input trials. That's a wrap on today's AI paper highlights. Thanks for watching.